Hi, I'm Gabriele Berton and I'm going to present the paper Rethinking Visual Geolocalization for Large-Scale Applications. This work focuses on the task of visual geolocalization, also called visual place recognition, which is the task of finding the location where a given photo was taken. This is commonly approached through image retrieval, where given a large database of images with GPS coordinates, the goal is to find the most similar match to the query. This work aims to solve two problems in the current literature. The first is related to the datasets, as we found that current datasets usually cover just a small section of a city. And the second is that methods heavily rely on mining, and the complexity of mining grows linearly with the size of the database, making it a non-scalable solution. So what we did first is introduce a large-scale dataset called San Francisco Extra Large. There is a database of 40 million images used for training, which is also used as a database at test time, when the final goal is to geolocalize 1,000 challenging queries. Now the problem is that current training methods cannot handle such large datasets because mining prevents scalability. So to train on such large dataset, we learn best practices from large-scale image retrieval. What is commonly done with datasets like Google Landmark is to have the images split into classes and then use scalable losses such as CosPlace or ArcFace to train the network. Unfortunately, datasets used in visual geolocalization have continuous labels, which are GPS coordinates, and cannot be easily split into classes. So our new goal is to learn to split the dataset into classes. Here is a representation of the dataset, where each one of these triangles represent a training image taken in a given direction. So first, we keep only the images pointing north. We split them into cells, and we remove adjacent cells, keeping only a fraction of the images. We then consider every non-empty cell as a class. In this example, there are 6 non-empty cells, meaning 6 classes. And finally, we can use this part of the dataset to train our network using CosPlace. Due to time constraints, I'm not going into details into how CosPlace works, but it's a module that contains a weight vector. It can plug into a neural network at training time, and then it is discarded at test time, and allows us to produce highly meaningful descriptors. So simply by doing something like this, we can see that we already obtain state-of-the-art results. I say something like this because in reality it's a bit more complicated, but this is the main idea behind how the training works. Now, although the results that we obtained were very promising, we realized that a large part of the dataset is actually never used for training. And so we tried to go even further. To do this, we simply discard the CosPlace module, shift the grid, plug a new CosPlace module, and train again. And we repeat this step multiple times. We call this method CosPlace. And now let's move to the results section. First, we found that for some previous methods, it is unfeasible to train on large-scale datasets. Others reach low results, while CosPlace can scale efficiently and reaches very promising results. Second, we showed that CosPlace is lightweight. Here the dimension of descriptors is on the x-axis in logarithmic scale, and the recall on the y-axis. Third, we found that CosPlace is very robust. We are able to vastly outperform state-of-the-art, previous state-of-the-art, when we move to very different datasets. Finally, here are a few more facts about CosPlace. We are 80% lighter on GPU than previous state-of-the-art. Training takes only 1 day on an 8 GB GPU. The code is open source and fully reproducible, but it has the disadvantage that it requires heading labels, while previous methods don't. So to summarize, our contributions are: we created San Francisco Extra Large, a 40 million images dataset, and we created CosPlace, a new scalable and lightweight state-of-the-art. So thank you for your attention. You can find our code on GitHub, and we hope to see you at the poster session 1.2.